Good morning or good afternoon. Thank you very much for your participation in this two-part training, Introduction to Population Grids and their integration with remote sensing data for sustainable development and disaster management. My name is Brock Blevins, ARSET Training Coordinator, and I'll be your host for this series. For those of you who may be unfamiliar with our ARSET program, we are part of NASA's capacity building program under Applied Sciences, and we are designed to empower the global community through remote sensing training. We have a variety of training types within these four application areas of air quality, water resources, disasters, and eco-forecasting. Our training levels are on the spectrum from introductory all the way to advanced, and this series is on the introductory level. This two-part training, developed and presented by members of the POPGRID Data Collaborative, will focus on the different population grids and their application to a range of topics related to development planning, monitoring of the SDGs, and disaster management. Briefly, the course structure and materials. This training will consist of two-hour parts, today on March 30th and next week on April 6th. The same content will be presented at two different times each day in order to reach more time zones around the globe. Note, you only need to attend one session per day. Webinar recordings, the presentations, and the homework assignment can be found on the training webpage URL, as you see here. There'll be a question and answer session following each lecture. Please feel free to type your questions for the trainers into the Q&A section. All the questions being asked will be moved to a Q&A document. You will be able to view all the questions and answers at the end of the presentation in a document and then answered audibly. We will then provide that as a PDF on our training webpage, generally within a week for you to download to use as a resource. You can also send your questions by email to myself at the email listed here or to the ARSET general Gmail account. There will be one homework assignment for this training, and they'll be given at the end of part 2 next week. These answers are submitted via a Google form. The deadline will be April 27th, and in order to receive a certificate of completion for this training, you have to attend both live webinars, so on March 30th and April 6th, and then complete the homework by April 27th. You will receive a certificate approximately 3 months after the completion of the course from Marinus Martins. So here's the training outline. Today, in part 1, there will be an introduction to the POPGRID Data Collaborative. There'll be background on the origins of gridding and its evolution from the earth sciences to present-day application areas in health, humanitarianism, development, and disaster risk reduction. Approaches to gridding, global to near global products and their strengths and limitations, as well as a tour of the online platform POPGRID Viewer will be covered. Next week, for part 2 on April 6th, there will be presentations of common research areas and use of population grids. Topics will include sustainable development, in particular SDG 9, as well as how population data sets are used in disaster risk reduction efforts. We are very pleased to have our two trainers here today, Stefan Leik and Greg Yetman. Stefan Leik is a professor of geography from the University of Colorado Boulder, and Greg Yetman is Associate Director for Geospatial Applications for CSIN, the Center for International Earth Science Information Network at Columbia University. So I'll send this off to you, Stefan. Thank you.
Thank you very much for this short introduction, Brock, and welcome everyone to this session 1 of our training in Introduction to Population Grids and Their Uses. My name is Stefan Leik, and together with my colleague Greg Yetman, we will cover this first session and give you an intro on existing population grids and the POPGRID Data Collaborative. We will cover different aspects of POPGRID, the POPGRID Data Collaborative itself, explain a few facts what this collaborative is doing. We will give you some motivation or explain some motivation for gridding population data, talk a little bit about methodological frameworks for population allocation and the creation of final data products. We will give you an overview of existing global gridded population layers that are open to the user community. We will talk a little bit about POPGRID's goals moving forward and give you a short tour of POPGRID's website and the POPGRID Data Viewer that can be used by the user community for quick data exploration. Finally, we will provide just a short insight on some application areas where population grids are useful and conclude with some final comments on data uncertainty and fitness for use concepts that are important to be concerned about for the user community and for the informed user on target applications. The mission of the POPGRID Data Collaborative can be summarized as being concerned about data for everyone. POPGRID brings together and expands the international community of data providers, users, and sponsors that are concerned with georeference data on population, human settlements, and infrastructure. They do this to improve data access for the user community, data timeliness, and data consistency, as well as utility. They support data use and interpretation. They support helping the user community to identify and address pressing user needs, to fully understand what are the requirements, what are the user needs out there. And finally, to encourage innovation and cross-disciplinary use. The main objective for POPGRID is technical and data advancement. POPGRID is trying this through new cooperation. They do this by channeling expertise from natural, social, health, and engineering sciences, from government, academia, and private industry, as well as NGOs. This unique cooperation promotes producing and harmonizing high-quality data services, as well as services that can be used by the user community. The POPGRID Secretariat is a collaboration of CESN, the Center for International Earth Science Information Network, TRENS, the Thematic Research Network on Data and Statistics, as well as GPS-DD, which is the Global Partnership for Sustainable Development Data. In more detail, POPGRID is trying to improve accessibility, documentation of datasets and services, to compare and contrast methods, as well as implications of different data sources, to fully inform data users what are the implications of using these different data products. To do so, they convene experts from the spatial or geospatial and demographic communities to have this expert knowledge involved, to understand how it's useful, for whom it's useful, and have a scientific basis. Finally, part of these goals are to provide online tools as well as services to facilitate visualization and intercomparison, and thus analysis for target applications. Here's a list of the data providers that are active in the POPGRID Data Collaborative. Again, you can see CESN, the Center for International Earth Science Information Network, the CUNY Institute for Demographic Research, the Connectivity Lab at Facebook, ESRI, the German Aerospace Center, the Joint Research Center of the European Commission, ImageCat, Oak Ridge National Laboratory, the US Census Bureau, as well as the World POP Program. The diverse group of members of this POPGRID Data Collaborative, which makes up and guarantees this new way of cooperating. There's a very interesting publication that came out in 2020 that we can recommend for users who are interested in using population grids. This has been published by Mariam Rabier and Hayden Dahn of the Thematic Research Network on Data and Statistics, as you can see it in this slide. And we recommend this for a quick information source, leaving no one off the map, a guide for gridded population data for sustainable development. It describes the most important or the central data products that we are talking about today, as well as some methodological basics, how these data are created and what the typical target applications could be and would be and have been. A few comments on the basic motivation before we go into methodological frameworks. The idea of rasterizing population has the goal to reallocate or partition census data that have been collected or that have been used for a long time. For example, a block group analytical unit, as you can see it here on the left. The goal is to reallocate population counts to, for example, grid cells, and thus finer resolution data where every cell holds a cell value that represents the population count at very fine scale or very fine resolution. So the idea of creating grids is to break down traditional census data to something like spatial distributions of population that hopefully can be used at finer resolution and allow us to use these data sources for fine-scale analysis target applications. Leaving no one off the map, to come back to this title, many applications in environmental sciences, sustainability, development are related to population. They are related to population at various scales. The big obstacle are census data themselves for such applications. Census data can be infrequent. The data might miss people. And this could be due to inaccessibility because of vegetation, land use, as well as topographic conditions, where there is no access for field workers, for example, as well as social constraints and language. Finally, census data are summarized very often for very large areas that can even change over time. See an example here in this white oval. This is a census unit for which we have to assume that the density, the population density, is equal everywhere because we only have one population count for this large area. What we really would be interested for many applications where the operational scale is much finer is a more nuanced population distribution, as here on the example of World POP 2014 in comparison. The big question is how we can get there. How can we rasterize or grid traditional census data into these kinds of gridded ways or gridded forms of population surfaces? Nowadays, we're using advanced geographical information science and remote sensing technology as well as data, and thus make use of the ongoing geospatial data revolution. These population gridded layers or population grids are not supposed to replace census data, but they are seen as complements, complementary information that can fill in gaps in time as well as in space, where traditional census data are very few in time for a certain time period or have gaps for the data themselves in different regions. More importantly, the estimates that we can derive from these population grids could be estimates for non-administrative units that could then be temporally consistent geographies at fine scale. One example is, for example, you might be interested in understanding how many people are living in close proximity to a stream, to a road, to a different water body, to a hazard zone. By doing this with census data, very often you have an effect, as you can see it here in this left side picture. The census unit itself does not allow you to break down how many people of these 241 are living close to a stream. Should we be successful in gridding population into these cell level or grid cell estimates, we are able to provide these kinds of estimates at fine resolution. If these population grids are reliable and accurate, then we can assume that these estimates are can give us a lot of confidence how many people are living in close proximity to our target feature. To illustrate this on real data, again, here for a region in Colombia, we have our census data, we have one count estimate, and thus we have to assume that population density is equal everywhere within that unit. Obviously, that's very unrealistic in many applications. And therefore, these population grids are so useful. They give us an impression of the variation, the underlying variation of population counts when we break it down to fine resolution data. Quick impression of the different data products. GPW, the oldest data product, the gridded population of the world, available for different points in time. Based on GHSL, the Global Human Settlement Layer, the Joint Research Center has published GHS POP, which is the population service derived from GHSL. The Global Urban Footprint has been used for deriving population layers. The High Resolution Settlement Layer, a collaboration of Facebook and Season to derive a very fine resolution population estimates. Landscan by the Oak Ridge National Laboratory, as well as WorldPop, produced by the University of Southampton in the UK. There's a wide range of applications that we can think of that this population data have been used already, and others, of course. POPGRID is very interested in spurring and encouraging more such applications in different fields, in different areas of scientific work, but also applied science. These fields range from land use to transportation, to resource management, resource allocation, to natural hazard risk assessments, climate change, as well as public health assessments. These population grids are also increasingly used for the development of international frameworks for development and sustainability. You can see 4 of the goals of the Sustainable Development Goals, or SDGs, where population is one of the most critical information to actually do measurements to understand underlying information, be it for sustainable cities, for poverty measures, or, for example, for the need of clean water or water access. I will speak about the methodological frameworks in the next few slides, just to provide you a very simple basis of what the underlying methods are, what kind of frameworks are existing. Basically, the creation of these different population grids are used or are produced based on data integration approaches, population allocation methods, to different forms of aerial interpolation. There are different top-down and bottom-up approaches existing in the recent literature. The aerial interpolation method is the underlying methodological framework for many of these kinds of efforts. The simplest method is aerial weighting. Dasymetric modeling is a slightly more advanced aerial interpolation method that is often applied using ancillary data in binary fashions or as empirical inputs. Statistical models, or statistical dasymetric modeling, that are often slightly overlapping with the more traditional dasymetric mapping, as well as hybrid modeling, where often machine learning is combined, is used, or ensemble prediction to produce population weights for dasymetric refinement. There's a bibliography at the end of this presentation where the interested reader can find many different sources on dasymetric modeling, on aerial interpolation, and other methods. Let us begin with aerial interpolation. It's been developed basically to address zonation incompatibility. The simplest method, aerial weighting, is probably a good starting point to understand the idea. In aerial weighting, we are trying to estimate source populations within target zones. Source zones A, B, C, and D are used to make an estimate of or within the target zone E, here in red. This method is based on the proportion of area overlap between the target zones and source zones. It's based only on geometry. You can see in this very simple equation that for each iteration which goes through different source zones, we are taking the source zone area, in this case for A, take the overlapping area of E and calculate the proportion of the target zone overlap divided by the source zone area. This will be multiplied by the population that is estimated for source zone A. Exactly the same procedure as carried out for each source zone to then come up with our target population for our target zone E. So again, this is based only on geometry, and therefore there are limitations because we assume that the population, the counts of people living in an area, is directly related to the underlying area, which of course is not realistic in many cases, but it's an interesting method that has been advanced, that has been refined over the years. Quick illustration how this works in practice. We have one school district right here, and we know how many students are registered for this school district. We would like to estimate how many students of this school district are living in different census tracts. We have two census tracts, 1 and 2. We know the areas of these two census tracts as well. The idea now of area weighting is to calculate the proportion between the area of census tract 1 divided by the area of the whole study area to come up with a proportion, as you can see here, of 0.709. This proportion is then applied by multiplying it with the number of students in this whole school district to have an estimate of students within census tract number 1. We do the same for sector 2 to come up with a second estimate, in this case for census tract number 2. Again, you can see that this estimate is made based on the assumption that there is the same density of students living in each part or in each section of this school district. Again, might be very unrealistic because there are different population groups living in different parts of such a study area. This method is volume preserving. As you can see, the target population estimates are adding up to the initial set, the initial count of students. This is called a pycnophylactic property, volume preserving. Based on these simple methods, asymmetric mapping has been studied for quite some time. It's another type of aerial interpolation to address zone incompatibility and aggregation. That's typically the case in choropleth maps. We're trying to reallocate population to mapping zones that hopefully reflect population distributions in more objective ways. We do so, that's the big difference, using so-called ancillary variables. There are limiting and related ancillary variables to make estimates that also are volume preserving. As I mentioned before, they are supposed to maintain the population counts in our source area. If successful, we might be able to calculate population estimates at fine resolution that show a more representative population distribution if the ancillary variables are meaningful and show us some strong relationships between these ancillary variables and population. Limiting ancillary variables are simple to use. They restrict the possible occurrences within the original unit where population might be living or not. Developed land or inhabited land might be just one example. Related variables or related ancillary variables are assumed to be associated with a variable of interest, population in this case. This association might be defined based on a set of rules, how the variable will influence our variable, or statistical relationships. And this could be economic variables, terrain-related information, road density, or other kind of variables that can be used in such models and are assumed to have a relationship to population. To illustrate the same case of a school district, this time with a limiting ancillary variable. Here we have developed land. We assume, in this simplified example, students can only live where we have developed land. The effect is a very obvious one because we can now adjust area to a different value. It's just the area of developed land within that school district. We can also adjust the area in each of the census tracts because we can refine it using the developed land. Everything else is exactly the same. We are calculating the proportion. This time, the proportion is slightly different as in the first case because we are just using the area of the developed land, and come up with a student estimate for census tract 1 that's slightly below the initial value that we had with aerial weighting. For sector 2, we do the same thing, come up with a value that's slightly higher than in the case before. So this makes it very obvious what the effects of spatial refinement can be in the simplest case of datasymmetric modeling, just using a limiting variable. To summarize, error weighting has the problem, or has the limitation, that every grid cell in this case would have the same value within one source unit. We assume equal population density, which is very unrealistic in many real scenarios. Datasymmetric mapping allows us to use ancillary variables, for example, to assume or to derive binary weights. We only allocate people where we assume people can live. Such a distribution would have a very different value for the different grid cells. Using more refined or empirically derived weights would allow us to create a more nuanced spatial distribution of the population, as you can see in this example. This might be, for example, different land use classes for which we derive different rules. How many people might be living in a certain land use class? Or we can use statistically derived weights, very often in regression form or machine learning form, where we are able to use several ancillary variables within the same model. Is one advantage. Second advantage is we can work with statistical inference in these models and hopefully create an even more nuanced spatial distribution of population counts at the grid cell level that, if the model is strong and robust, has very reliable estimates and provides very accurate estimates at fine resolution. In other words, datasymmetric frameworks are very dependent on ancillary variables. It's very important to identify whether or not there's a relationship between these ancillary variables and population. The user has to be aware that there might be temporal mismatches between ancillary variables as well as the population, and how to address that. There might be even temporal mismatches between different kinds of ancillary variables. Furthermore, it's really important to understand the quality of these ancillary variables. What is the spatial granularity, for example, of elevation if we use it, or protected areas? What is the underlying mapping scale of road networks that are used to derive, for example, road density or the distance to roads? These are all possible data or ancillary variables that have been used in the literature for a long time and have been proven to be effective in regions where we might not have fine resolution enough data. This table provides an interesting overview on how many ancillary data or ancillary variables are used to create the different population grids. You can see the population grids that I mentioned before, and it's interesting to see how they differ in terms of what kind of ancillary variables are flowing in to the creation of these different population grids. This is directly connected to the methodological framework used for each of these population grids to be produced. Greg Yetman will now take over and talk more about the global gridded population grids that are available to the user community. Greg, please.
Thanks very much, Stefan. Glad to be here today. I'm going to talk a little bit about the list of global grids you see on the screen here, and we're actually going to dive a little deeper for each of them and look at the data in a little bit as well. So just to step back and introduce myself, my name is Greg Yetman. I'm a geographer at Season, and I've been working with gridded population data since the early 2000s, so quite a while. So here on the screen, we've got a table showing the different global data sets. And when this is posted, the name hyperlinks to each of the data sets on the organization's website. And one of the questions we get most often is, how do I choose which data set to use for my analysis? And I'm going to quickly go through some of the high-level considerations for choosing your data sets. So when you look at resolution, you may think, oh, well, I just want to pick the highest spatial resolution to get the most detail. And that may be the case for some applications where you're working very locally. But there's an important point to that, which is, if you're doing a global analysis, for instance, working with 30 meter or 90 or 100 meter data can be taxing to do on even a modern desktop or laptop. And if you need a time series, some of the highest resolution data sets don't actually have a time series. They're just a current year. So for instance, if we go down the list and look at the resolutions, they vary everywhere from 30 arc seconds or roughly 1 kilometer for land scan and gridded population of the world, or GPW, to a moderate 250 meter resolution, 150 meter resolution for GHS POP from JRC and the world population estimate from ESRI, respectively. And then the more detailed data sets you get are world POP, which is about 90 or 100 meters, 3 arc seconds globally, and the high resolution population density maps, also known as HRSL, which is down to 1 arc seconds or normally 30 meters. Now, the HRSL isn't truly global. It covers about 160 countries and territories in the world, so a lot of the world. And there is a release due out this year that'll cover even more countries. The rest of the data sets here are global insofar as they cover the inhabited Earth. Most exclude Antarctica, which I think is fine for most applications. The other thing to consider is what time periods you need and whether you need to look at change. So the GHS POP and World POP, which have epochs from 74, 90, 2000, 2015 for GH POP, and annualized 2000 to 2020 estimates for World POP, are your best options for actually looking at population change. GPW has a series of estimates, but it's not a true population time series because it's based simply on proportional allocation. So the time series change is a growth rate between 2 points in time that's interpolated or extrapolated. So it's not ideal for a time series or change in population over time. It's more about picking the year that's closest to your other data sets that you want to use it with. And then finally, the most complicated part is to look at the model. So the simplest model is gridded population world, which is just proportional allocation or areal weighting, where the population is distributed equally across the admin units that are in the GPW data collection. And one of the reasons we produce the data set this way is that it is the simplest possible model and independent from any other biophysical or remote sensing derived variables. That is, it doesn't use something like distance to coast in the model to allocate population. So if you're interested in assessing coastal populations, you don't have to worry about endogeneity. You don't have to worry about the model being biased towards population near the coast. The same is true for other variables like elevation. While the more heavily modeled surfaces, like the land scan, world population estimate, really do a lot of moving population around within administrative units based on the other variables. So they are likely a more realistic distribution of population, but they use a lot of different variables for that. So you have to worry about endogeneity if you're trying to study a particular phenomenon. But if you're just interested in, for instance, a hazards assessment, those more modeled surfaces are probably more useful. And the GHS POP is machine learning to detect settlement extents and then weighted allocation or a binary daisyometric approach to allocate population to the settlement extents from Landsat data and more recently higher resolution 10 meter Sentinel data. And the high resolution population density maps, the HRSL from Facebook, actually use the highest resolution input data. It uses 50 centimeter to 2 meter optical data from Digital Globe, now known as Maxar, to find settlement extents, and then a similar approach of weighted allocation or binary daisyometric allocation to assign census data to the settlement extent. And because it's got such detailed optical input data, it is the best data set to look at rural population distributions because it finds many small settlements that it can't be found in lower resolution inputs like 10 meter or 30 meter Sentinel and Landsat data. So next, I wanted to quickly look at POPGRID's goals moving forward. So listed here are directly from the POPGRID website, a longer form of the goals that Stefan showed earlier, so I'm not going to go through them in detail. But the important thing is for us as a collaborative to provide a great space for people producing these data sets to collaborate and share methods and agree on standards, and users of the data set or data sets or tools that are based on the data sets or have the data sets as inputs to understand the implications of using the different data sets and selecting the one that's best for their purposes. And we've taken on a role of support of use of gridded population data for international groups from the UN, specifically under the SDGs and indicator measurement, different aid agencies, private foundations, and any other communities that are using the data for development or even commercial applications. The other thing that is a little outside of our focus today, because it's not related to population data set, is infrastructure and training data. So an example would be different groups that are trying to classify settlement extent by detecting buildings through POPGRID have met and talked and shared training data sets, like the location of known buildings with the date the building was present, so that training data, which is expensive to generate, can be shared in across groups in the collaborative to make all the data products better and save essentially resources for all the groups that are in the collaborative. A second part of it is infrastructure data is an aim of the POPGRID Data Collaborative, including things like building extents, roads, and building characteristics such as level of built up or number of stories or construction type, which is important for things like hazards modeling and lots of other research. Here's an example of what we've been producing to support end users, including academic papers and reports. This is a preprint that was put up just last month by Dana Thompson and a number of folks in the collaborative to assess the different gridded population data sets related to estimates of slum populations or informal settlement populations available in parts of Nigeria and Kenya. And what we found is that the gridded population data sets, all of them, consistently underestimate the population within slums based on the ground survey data. So the amount varies, and the paper details which gridded data sets are closer to the estimates on the ground compared to others, but it's no surprise the very lightly modeled data sets like GPW4 and GHS POP are sort of the largest underestimates of distribution population totals in slums, while the more highly modeled population surfaces do a slightly better job of doing that. HRSL, for instance, gets about 40% of the population in the slums, while other data sets like GPW are down to 10% or 15% of the population overall in the slums. So the populations in slums, understanding and knowing the distribution of that population is important for the SDGs and lots of other development projects. So the point of this paper is that these data sets as is are not the best options for looking at slum populations. And we've made suggestions in the paper about different modeling approaches and how additional data could be used to augment the models to produce a more realistic estimate of slum population using gridded approaches. Now I wanted to do a quick tour of the website and POPGRID Viewer. So if you go to the POPGRID website, I'm going to full screen this here and go home, we're going to see that there's an overview of the project, but I think most important is this Explore Data tab. And we'll start looking at global population characteristics. So we can see similar to the table I had in PowerPoint, but with much more detail. You've got information on each of the gridded population data sets available for global data. We also have continental and country gridded population data sets. These are data sets that are not necessarily global, but maybe of interest because they're available in the areas you're working in with the same kind of information shown for each. And then we also have descriptions of settlement extent, gridded settlement extent data, which doesn't necessarily have a population estimate, but a comparison of the time and the resolution and the source data for each of these settlement extent data sets. And probably most useful for getting a quick look at the population data is to go to the POPGRID Viewer. This is supported by CDAC, the Socioeconomic Data and Application Center, that we at Season operate for NASA. And you can see linked maps that show you 5 of the different data sets, 4 by default, and you could switch up which is shown. So all of these data sets are available. It's more than 5, correct myself. And you can compare any 4 to look at population. So for instance, if I go into Central America, and if I click on a pixel here, it will tell me the actual pixel value from each of the 4 data sets that I have visible. And you can see it varies widely from GPW, which is low and likely an underestimate, up through the max value being from Landscan, which is a highly modeled surface. And you can, of course, like I said, switch these out, but and pan and zoom around and look at the population data anywhere, and even zoom in pretty close to see how the distribution varies, and see the limits of something like GPW based solely on census data. It starts to look just like the census units versus GHS or World Pop or Landscan. Or I could switch this out and show the high resolution settlement layer. Here it is, the high resolution settlement layer aggregated to 1 kilometer, so it's directly comparable. And you can see how the distribution looks for these heavily modeled surfaces. And then if you've got an area of interest, let's say we're interested in how many people live in this city, you can flip to a comparison view, and we'll get a help screen that shows you how to use the comparison view, but I'll leave that closed for now. And the population data layers that are available are shown here, and we can turn off GPW. We'll turn on our GHS pop, and here it comes up. Here's the GHS pop, and here's the city, and I could draw a polygon around this city. Just roughly estimate that this is the city area, and it will submit that polygon to the server, and I can hide the help because I don't need it right now. And right now it's taking about 20 seconds or so to process each of these jobs. We're actually working on rolling out new servers that should hopefully make this a slightly faster process. But then you get a bar chart showing you the population from all of the data sets available in this area from partners in the POPGRID Collaborative. And you can mouse over and see the total population from each data set. And we can see how it varies from 490,000 all the way up to 1.2 million from Landscan, or 1.2 million from, we have 2 versions of Landscan, 2015 and 2018, or just over 1 million for World Pop. And of course, all these data is a table that you could copy and put into a spreadsheet or a report. And we've got some data quality measurements. The ESRI World Population Estimate has a reliability ranking, and it's ranked at 2, and that's documented on the data set what those reliability rankings mean, but that's a pretty good reliability ranking. HRSL has coverage. It's not global, but it has coverage here where we do the polygon. And our GPW data is using admin units in this area with an average area of 433 square kilometers, which is not very detailed. So the GPW estimate is, I strongly suspect, an underestimate. And so you could repeat this exercise from anywhere that you want to do a population estimate by drawing a rectangle or drawing a polygon and getting a good look at the population estimates across. Lots of folks have asked, well, why wouldn't I do this and just average all the population estimates to get a more reliable result? There's 2 issues with that. The first is that a number of the data sets are using the same census data inputs. That is, specifically the data inputs used for gridded population in the world, GPW, are used in the HRSL and the GHS POP data set and the World Pop data set. So the estimates you get for a total that includes a whole or multiple admin units are going to be, if you average them, are going to be biased towards the GPW estimate, which may not be ideal if the data for the country in particular that you're working in, or countries if you're crossing a border, are not as reliable. They vary in GPW country by country, and that's documented on the website as well. So here we see for this larger area, the population estimates are in closer agreement, between 450,000 and 570,000 or so. And you've got the same sort of quality information available for that. So that's a quick look at the POPGRID Viewer. There are other capabilities. One more I want to show you, but we'll come back to it, is the ability to upload a shapefile. So next I was going to take a quick look at QGIS. And here in QGIS we have administrator boundary data for Colombia that I've preloaded. I've even subsetted it and made administrative boundary data just for one area of interest inside of Colombia. And I exported this as a shapefile and zipped it up. So there's a shapefile on my hard drive that is just these admin units in a zip file. And what the POPGRID Viewer allows you to do is, if you click on the shapefile tab, you can choose a zip file that has your shapefile. And here's my zip file with my Columbia admin2 subset.zip. When I open that up, it will validate the shapefile. And it notes that my shapefile contains multiple polygons, and it actually merges it into a single polygon, which may be not exactly what I want to do. But here is the result. Here's the polygon that's merged from all those polygons. And you can see we're just north of, I think it's just north of, I forget which city, north of a city in Colombia. And you can see the pop estimates for all these polygons, right? So they vary again from 800,000 to 1.2 million across all the data sets. But if I was interested in pop estimates for each of these individual polygons, there's a way to do that as well, but it takes a little more work. I'll show that. And then the next thing I wanted to show you is the ability to look at the map services that are behind this directly in QGIS. So here we're looking at the map services. This is the GHS POP for this portion of Colombia. And this is coming off a ArcGIS server instance. And here's our ArcGIS server that's available from Season. And if we go into the Season folder, there's actually a series of services for POPGRID. And there is the Season POPGRID Counts map server. So this is a map server that shows us population count layers for each of these. What I can do simply is copy this URL, and in QGIS we can make a connection to that URL. So if I go to layers and add a layer, I can add a ArcGIS REST server layer. And that's just what I was looking at in the web browser, was the REST interface for ArcGIS server. So I'm going to make a new connection. I'll call it POPGRID, and I'll paste in that URL that I copied. And that's all it takes to get access to the layers. And so now with POPGRID, I can click connect, and it connects, and it shows me all the layers on the server. And so I can go and add those to my map. So I'm going to add the GHS POP count, the GPW 2015 count, the HRSL count, Landscan 2018, and the World POP 2015 count. I'll add those in, and they show up with the legends, although because my using the darks theme, the legend itself doesn't show up. And the first thing I'm going to do is actually turn them all off and start with the GPW layer. Hopefully it will redraw for me. There it is. So if you look at the admin units that I'm using here, they're from GeoBoundaries. You can see that they actually match the census units that were used in GPW to do that proportional allocation. So doing a sum here would just give me the total pop per admin unit based on the GPW census pop, which is not necessarily a terrible thing. But more interesting is looking at some of the other distributions. If we look at the HRSL, and especially if you're using units other than the admin units, you can see a lot of variability in the distribution within the admin units that I've got here. So if you're using a different than the census admin units, you get a much different picture. And then LandScan shows you a different picture yet again compared to the HRSL and GPW, and it's got a much more heterogeneous prediction. One of the things I should mention about LandScan is one of the prime reasons you may be interested in using LandScan is that they predict what they call ambient population density. So GPW and HRSL and anything that's based on a top-down census approach is essentially using census data, which is where people live or where they sleep, nighttime population distribution. LandScan uses census data, but they use larger admin units and rely on the model to distribute people across both commercial, industrial, and residential areas. So you get an average population that accounts somewhat for how people move about during the day or week. The World Pop model is smoother than the other ones, but it does show, these peak densities that really are more realistic estimates than the simple GPW. And so that's how you can use the layers without having to download and visualize all of these data layers yourself from inside QGIS or ArcGIS if you're an Esri user. You can of course access these services and visualize the data. And then the final thing I wanted to show in our demos here is I stood up on GitHub. So this is a public GitHub repo. And if we go just to the root, here's the URL you can use to get just to this public repo. And it's a demonstration of getting estimates for each of these layers. So here's the same subset file, right? I recognize these from QGIS. This is just north of Bogota, these admin units. And there's a Jupyter notebook here that demonstrates how, without GIS and without any additional modules, just straight up Python, we can lob a request at our server and get a population estimate for all of the polygons, individual polygons. So if I follow that link, we can see that the server service takes this type of input, which is a polygon. It only accepts one polygon at a time. And variables, that is the layers you want to get population sums for. And statistics, you can get the sum and or the mean. And a request ID, which is just a unique identifier. So if I go to the live version of this Jupyter notebook, which I'm running on my laptop, if you're familiar with Python, this should look familiar. If you're not, I wouldn't worry about it too much because we can't parse all of this Python in a short demo. But I can import these libraries, which are standard libraries that come with any modern Python install. And I can open that Columbia JSON file. And I just, this is the way live demos go. It's in the data subfolder. So I can import those libraries and then read in the JSON file, and we can see that the JSON file has types, has a type, a name, a coordinate reference system, and features. And the features are the polygons that we saw for Columbia. And then this largest block of code essentially sets up a container to hold the results. And then for every feature, I build a request that is very similar, actually pretty much identical, except the coordinates are different, to this request, example request here, where I give it the coordinates, I tell it I want the GHS population count, the sum, and the mean. And that's what this block does. In a loop for every feature in the input file, it makes that request. I then, actually, this is the bit of code that makes the request. And then the request is returned, and I handle the output. And if there's an error, it's going to print error. Otherwise, for each admin unit, it tells me that the request was successful. And it looks like we're hitting the server at a good time. It's not overloaded because all the requests are successful. So I can look at the output for one particular request. This is the unique identifier that I supplied, and see that I get a response, data type. Most useful is our short title. This is the Landscan population count for 2015, which is what I requested. The unit in persons, and the mean, and here's the sum. I overlooked the sum. So for this particular admin unit, it's estimating that there's 13,000 people, according to Landscan. I can then pull out the totals, just the sum. So I'm just pulling out the sum from all results and plot it. So here's a histogram across all the admin units showing the population and the number of units that fall in that bin. More useful might be just a simple bar chart. And I can plot that with just 3 lines of code. So here's each of the admin units and the population estimate from Landscan for each of those units. I could save this out and open it in Excel, or join it back to my shapefile or feature class in QGIS and map with it, or do whatever I like. So a really simple demonstration on how to use basic Python to get results from our server. And this is the same service that I demonstrated for drawing a single polygon in the web and seeing the results. So I'm going to finish the demos, or I've finished the demos, and I'm going to go back to PowerPoint and continue on with the presentation. So to discuss some application areas for population grids, there's a list here on the left that shows us common applications: hazard exposure, exposure to potentially high impact earthquake areas, modeled flood surfaces, areas that could be exposed to drought, any type of hazard. It could be a technological hazard as well. You can use gridded population to take that irregular area of higher hazard risk and estimate the number of people that reside inside that area. There's a really common use case for health service delivery, including things like vaccines, delivery of polio vaccines in Africa, Ebola vaccines, has used gridded population data to estimate the number of vaccines needed and the labor force to deliver them, and even down to routing in combination with street networks to reach the maximum population efficiently using gridded population road networks and known transport modes. It's also been used for health facility planning, looking at existing health facility areas and estimating how many people can be reached within a certain time period from the existing health facility, and identifying gaps, places where additional health facilities should be placed to cover more population. Monitoring of population change for things like the Sustainable Development Goals. As some of the data sets have a time series, and many are produced on an ongoing basis, you can look at change over time from some of them. There's been lots of commercial applications from planning cell phone networks, or even just looking at the potential market for cell phones or other services. Gridded population has been used for that, and it's been used in human environment research for a long time. So some examples here just below, we have what's a global study known as the Low Elevation Coastal Zone that was produced at Season, where we took SRTM-derived, the Shuttle Radar Topographic Mission, elevations, and we took that global elevation surface and found all the areas that are adjacent to the coast in different bands of low elevation. 0 to 3 meters, 4 to 7, 5 to 10, or greater than 10 was left out of the study. And then we could calculate the total population in each of those low elevation coastal zone bands by country, or globally, or by continent. So here's a map of the population density. This is the Nile Delta where it enters the Mediterranean Sea. It might be difficult to read, but that's a line pointing out Alexandria. And the gist of the data set is that you can systematically assess globally, internationally, the population that lives in the low elevation coastal zone that may be exposed to potential impacts from sea level rise or more frequent storms, so coastal flooding events. Here on the right, we've got, this is a link to a story map that shows you different ways you can measure SDG 9.1.1, an indicator that measures the rural population access to roads. So we took different population data sets and different subsets of roads data sets for Africa and computed the proportion of population that had access to all-weather roads by admin unit. So the grid population were used for the estimate, and we aggregated it up. So in red, you can see essentially are the admin units that have a relatively high index value for the population not having access, the rural population not having access to roads. And so the story map walks through the different methods and the different data sets used to produce it. For Northern Africa, we're actually working on producing that data set globally so that SDG 9.1.1 can be compared across countries at a subnational level globally. And as new population data sets are released, new grid data sets that are suitable, and new roads updates are made to roads data sets, we can rerun the global analysis and track change over time that's due to actual change in population and roads, and somewhat due to improvements in the data sets. And then finally, I wanted to show some an older paper. This is by Small and Cohen. Chris Small is a researcher at the Lamont campus at Columbia, and Joel Cohen is a researcher in the population center on the main campus at Columbia University. But this is work done in 2004 with gridded population in the world, just looking at basic distribution of human population across the Earth's surface. And the takeaway from this graphic on the left, this plot on the left, is that if you look here, the percentage of population, about 2/3 of the world's population lives on less than 5% of the Earth's inhabitable surface. So we are really a clustered population distribution. The larger plot shows you the global distribution, and you can see that as you get up to about 2/3 population, you're somewhere over just 5% of the world's surface. And this is done with GPW just by adding up where the densest populations live compared to the total land area. So inhabitable land area is just simply land surface area that isn't permanently snow, ice, or water. So a pretty simple assumption there. And then it was repeated for distance from permanent rivers by altitude, that is elevation above sea level, and distance to seacoasts. And so you can see that people generally live, if you look here, the sum of population, most people live close to a river at low elevations or close to a coast going across. Everything shows a descent. The exception here are some high altitude cities like Mexico City that cause this spike around 2,000 meters. But again, the majority of the population lives close to permanent rivers, at lower elevations, and close to the coast. And these assumptions are built into some of the dasometric and more advanced machine learning models, because things like distance to river, distance to coast, and raw elevation are included in the model parameters. And this is why, because people are associated, residential population is associated with these phenomena. And then finally, some remote sensing derived climate norms, temperature and precipitation, you can do the same sort of analysis and look at where people live according to average annual temperature, and you see a spike. Most people living within a range of average temperature of 10 to 20 degrees Celsius. And here, the same plot against annual range, you see the range varies more. And if you look at precipitation, most people are living in areas that get 800 or so millimeters or more. And then in very wet areas, the population actually tails off. And then if you look at the variability of precipitation, more people live in areas that have more variable precipitation, which is not a surprise when you look at human distribution. You see a lot of variability in temperate areas, which is where a lot of the population lives. Temperate and subtropical areas have a lot of annual variation in precipitation. And that's where most people live. So that's the end of my section on the tour of population data. So Stefan, I'm going to hand it back to you and let you go on with uncertainty and fitness for use. Thanks.
Thank you so much, Greg, for this excellent overview. I think this was a great overview of different applications and how to really work with the population data in the web viewer. Thank you very much. And I want to conclude this presentation with some words on data uncertainty and fitness for use. These population grids are a very special kind of data, as everybody will experience when they are downloading them and looking at them and comparing them. POPGRID has been investing quite a little bit in intercomparison frameworks. And that basically means to take all the different data sets and compare them. You can, or you could see this already in some of the examples that Greg was describing, to basically take the different population grids for the same target application and see what you find. And it's really interesting to see different trends, typical patterns, see a relationship to the underlying scale, for example. And all this has been reported in quite some research already and needs to be collected systematically to better understand what kind of data are used in what way and what are the general trends that different people see repeatedly. That's a very effective strategy to better understand what is the implication of using certain data sets. Here's one example from 2019 Tucholsky et al. On the total population by settlement size for Africa. You can see in this case the 4 population grids that are compared here show very interesting patterns. The user, after seeing these, is then probably very interested in understanding a little bit more. Why do I see these trends? Why do I see these radical differences? And it would be always a good idea to explore some of the reasons why that might be and what data sets seem to be an appropriate solution for your target applications and which do you have to treat with a little bit more of some care. Validation efforts in and of themselves for population grids are very difficult. They can be done and are done and will be done in more frequent ways wherever we have high quality data available. That's really important to understand a little bit more about the real accuracy of these grid population distributions. However, for many countries, obviously, these ground truth data or reference data are not existing because we begin with a problem of highly aggregated census data, poor data coverage, if any data at all, for a long time period. So we always will have this effect and this central problem of not being able to validate the data themselves for large regions where they are actually being applied. However, the intercomparison strategy is a very effective one to at least understand how the data behave for different target applications and at different scales for different regions, for local applications, etc. A very effective approach to evaluate the data a little bit more in depth is the so-called concept of fitness for use. Here we are trying to use the context of target applications to better understand what are the data used for. Is it an appropriate use? Should the user be careful about it? We basically want to inform the user about forms and appropriate, uncertainty-aware use. The concept of relative data quality, or as we call it, fitness for use, describes how we can assess the appropriateness of a given data set for an intended purpose, as I mentioned. Important is to guide and inform the user community while they're making informed decisions, or at least make sure they can do informed decisions by better understanding the aspects of accuracy. And we're talking about spatial, thematic, and temporal accuracy of these data in relation to the intended use. And that's exactly the key of this kind of concept. It's very important to understand what kind of input population data am I using. You remember Greg was showing you the input data being used can be of very different qualities. It's very important for the user to be aware of what exactly are the input population data that I'm using. The modeling assumptions behind the products. It's very important to understand, is this a heavily or highly intense modeled data product, or is this underlying very simple and simplistic assumptions of just proportional fitting, for example? And third, we have ancillary data that we're using, and the user needs to be aware of what these kinds of data really are and what they have to be concerned about and should be taking into their interpretation of their results. So data aspects and relative quality, to begin with that. There's aggregation effects. I talked about this for quite some time. That's really important. What are the aggregations of input data? Now I'm talking about the population data, but also what are the mismatches between different data, population data and ancillary data, for example. And what is the inherent variation? Can I even estimate the inherent variation of these data? I might use different qualities of input data, population, or ancillary in different regions, in different countries. So this boils down to the questions of scale, of currency, how much in time or how much temporal overlap is there between the data, and semantics. What kind of populations are actually modeled? Greg mentioned there are different target populations for different data products that can be modeled, and the user has to decide what kind of population is the target population in my application. I'm back to scale. One more illustration of something that I've mentioned before. Whenever we are using census data, we have this high aggregation of, underlying an assumption of equal population density anywhere within that unit, which we know now is unrealistic. Now, we can choose from different data products that are available, for example, GPW, for example, WorldPop, or for example, GHS Pop, or any other layer that we might be interested in. Here we go. So it's really important to understand the differences, to understand what the data really are displaying per grid cell, what is the underlying spatial resolution, and how does this relate to my target application scale. There's an operation in scale at which I'm assuming my target variable or my process I'm trying to model, be it, for example, for natural hazard risk exposure, or be it for accessibility to water resources, where I would like to have population grids that are as close as possible to that so-called operational scale. Very often I have analytical scales that are coming with the spatial resolution of these data, and the user has to decide, is that an appropriate scale, or is my scale, my resolution too coarse to actually work at this operational scale? And finally, the processing and model-related implications of uncertainty, data integration frameworks, population allocation methods, as we described them here in this session, they have consequences. And depending on the modeling intensity, I might have robust estimates, but I might also not be able to make good statements about the quality of these estimates. They are still at very fine resolution, but based on the input data and based on ancillary data available, the estimates might actually have high local errors. So these are all aspects that the user needs to be aware of and find ways of how to evaluate this. Are there really large deviations and differences when I'm using different population data, and what might be a reason? Also, there's the effect of uncertainty propagation. If I'm using complicated models, complex data processing procedures, well, I'm basically creating uncertainty at different ends of my analytical chain. And I would like to understand what is the propagation of this uncertainty to my final and target application. Finally, our ancillary data we mentioned before, it's really important to understand what ancillary data have been used. Have there been used, for example, road networks, or not at all? What about streams? What about other really important elevation data, for example, that we mentioned before? And what is their quality? For example, the underlying map scale of road networks and hydrography. Or what is the completeness and resolution of underlying ancillary data, for example, settlement, that I'm using for spatial refinement of my population estimates? All these are important aspects that feed into the quality, into the relative quality estimates that I have to make in terms of, is my application a reasonable and an appropriate application for the population data set, for the gridded population layer that I'm intending to use. Based on these kinds of insights, we try to formulate some interesting questions that we believe will help the user community to inform themselves and to be better instructed on these critical aspects of the data that they have to take into account while downloading the data, using the data, and following through and trying to carry out their projects and target applications. For example, how important is spatial refinement of the population grid to be used? Do you really need a 100-meter resolution, or is your target application of different nature? Do you just need a regional level, a regional scale being applied there? Different data sets might come into mind and might be appropriate to be used. Does the analysis focus on urban populations? A very important question, because many ancillary variables in many different countries would have higher quality in urban settings naturally. Rural settings are very often more problematic because the census data are sparser or they are more incomplete, as well as the units might be much larger than in urban areas that I'm using as input population data. What is the target population for the question at hand? Of course, as Greg mentioned, there are different target populations that are modeled in these different products, and the user might make a good decision or being interested even in testing these different target populations, because this might inform their application as well. Is the population grid being used to model other outcomes? That's really important. Greg mentioned this as well. You have to be aware of what ancillary data have been going in to these different population grids. For example, if road density has been used to asymmetrically refine population counts, you should not try to analyze road density or road-related variables in your target application. Finally, are you analyzing change over time? As mentioned before, there are different population grids that are available for different points in time. Others, not so much. They cover different points in times. And of course, the multi-temporal nature of these population grids might be different as well. They might depend on each other. They might have some temporal interpolation processes inherent, or they are completely independent. All these are aspects that might be important for your target application. The final one, how have these data sets been used previously? And we believe this is a very important one, especially while more and more application examples will be published in the scientific and applied research communities and outlets, where users and potential users can see more and more examples of how these different population grids have been used in the past. And hopefully they will refer to peer-reviewed and reliable studies and analysis where we have some quality control that different users have thought about this. And the more critical users there are out there of using these data sets, the better informed novel users and potential users will be in the near future. With these concluding words, the last thing I want to mention is this publication that we produced in the name of the POPGRID Data Collaborative. You can see many of the members of the POPGRID group are co-authors on this publication in Earth System Science Data, which is basically the publication of much of the content that we produced and that we presented here today as a second source for those who are interested in understanding more and reading more and finding more reference sources about these methodological frameworks and applications at hand. Find a short bibliography here at the end and find more information in some of these publications. With this, we would like to thank you very much, and in the name of our team, appreciate much your attention. Thank you. And with this, we will now transition to our question and answer session, and we're more than happy to answer any questions we might, and are very interested in your opinions and very interested in your potential applications. Thank you very much.
Okay, we will be transitioning to the question and answer session. Thank you very much, Stefan, and Greg. That was a very detailed session about an introduction to these population grids. So we have been transferring the questions that have been asked throughout the session over to this question and answer document. Please keep typing your questions as we go through these. So without further ado, I guess I'll just start off with the first one here, and I'll leave this to either Greg or Stefan or Susanna, whoever is most appropriate to speak to these answers. I'll start off with the first one. Question one, may I know the difference of this between and CDAC?
Hi, Brock. I can take that. Yeah, CDAC is the NASA-funded data center that is operated by Season, and it participates in the POPGRID Collaborative. But it's not. It provides resources to support the POPGRID Collaborative, including the website. But the collaborative is, of course, a member-based organization that's coordinated by 3 of the partners, as Stefan mentioned.
Great, thank you. Question 2, is there a method to extract a specific area of gridded data and regrid the small area using Python?
I guess I'll take this one again since I did the Python demo. Yeah, it's possible using Python libraries, either ArcPy if you're an Esri user, or QGIS Python libraries, or something like Shapely and Fiona, which lets you work with geometries, and Raster IO that works with raster data. And it's possible just inside of desktop GIS as well. And the general approach would be to extract the population from the grid or grids for the polygons of interest, and then regrid at your chosen resolution by a simple, well, there's 2 methods to do it, but essentially the general one is convert the polygon to raster pixels and count the number of pixels and multiply it by the density, and you get an area estimate for each pixel. Additionally, you likely want to at least use daisyometric weights from other layers, or you could use machine learning approaches or other models to predict population and then regrid the totals from the grid from the existing global products. It's been done several times by different groups. The other way to do it is, of course, take the vector of census data and grid that at a different resolution. But I can provide more details offline. It's quite a lot of detail to get into in the code.
Understandably, thank you. Number 3, could you be a little bit more specific about missing people in the census?
Yeah, I can help answering that question quickly. It's well known that there are different levels of error in different population censuses, which this basically means is we are trying to enumerate the target population in different countries, but the coverage is very different, very often not 100%. So that's one of the arguments to be made in there. The users can see more information in some of the publications that we indicate in our presentation, in our bibliography. Of course, there are also reasons such as limited accessibility. There are conflicts in different countries. It's very important to realize these are global grids, and the coverage temporally and regionally can be very different across countries. And that's what was meant about missing parts of the population at different time periods for different countries.
Great, thank you very much, Stefan. Question 4, what is the resolution of the grids? And I'm guessing they're talking about spatial resolution and the accuracy levels of the data.
Yeah, so the resolution varies from the most detailed being the HRSL at 1 arc second, or approximately 30 meters, all the way up to 30 arc seconds, with also products at 100 meters, 150 meters, and 250 meters approximate resolutions. So it varies quite a bit by product. And for uncertainty, we've done intercomparison of different products to look at how reliable they are, often compared to each other or a separate, more detailed source of data like census data inputs where they're available, which is not everywhere, of course, to come up with numeric and relative measures of how the different products qualify. But there's no one reliability measure. I think we've got another question on reliability where I talk about some of the products, GPW, WorldPop, and the Esri World Population Estimate all have pixel level quantitative measures of reliability that are not the same, but give you a per pixel measure of the relative reliability of the data products that you can use in your analysis.
Okay, and question 5, how frequent is the data updated, considering the fact that different countries conduct their population and housing censuses at different years?
Yeah, so I had to go with this answer as well. So it does vary a lot by data set. GPW is probably the least frequently updated because it's relying on the census, which is typically decennial rounds of censuses that happen around 2010, 2011, and then are happening now, 2020, 21, with sometimes estimates or census data being released, in odd years. But we tend to do roughly every 5 years a big update of GPW. Then other products like the Esri product and the HRSL are done annually or biannually, along with Landscan, which is done annually as well. And one of the reasons you see more frequent updates is not because there's new census data globally, although they may be able to take advantage of updated census releases for some countries. It's because the remote sensing derived and other input variables that they use in their models are updated much more frequently than the census, so they can show change based on the other variables, if not the census. And also they can they often improve methodologies between releases. So both the Esri and the Landscan data are produced fairly frequently, but each edition is not directly comparable with the previous edition because there's always been to date updates in the methodologies. So the two data sets are not directly comparable. So you can't do a change product, for instance, even though they're produced fairly frequently.
Great. Yeah, that was a great question. I'm sure a lot of people had this same sort of question. So thank you for explaining that. And this kind of goes into what you were discussing in question 4 about reliability. What is the simplest method for grid reliability analysis?
Right. Yeah. So as I mentioned in the previous question, some of the data products publish reliability measures on a per pixel basis. So for all of these, you can, for example, do a zonal statistics, like I showed in the web application, where you get those quality measures, those reliability measures, just by drawing a polygon. You could do that in your GIS or in code as well, or just via the website. And it tells you, for instance, with GPW, the lower the mean admin level unit size that's in the area you're interested in, the more reliable it is. And with the Esri reliability measure, it's a dimensionless index 1 to 10, and you can just use that as a relative measure of the reliability measure there. And then with WorldPop, they have a standard deviation. So you could even multiply your standard deviation by your population estimate, or simulate a 95% probability distribution of your estimate with WorldPop data, and see what your error bars are on that data. And then finally, there's several papers that are linked here that estimate the reliability or describe the differences in reliability across the grid of products by comparing with more detailed, or see Stefan's paper from 2019 for a good summary of all this.
Great, thank you. And it looks like that reliability validation kind of goes into question 7 as well. And I just want to say that I posted these links to the articles in the chat box, and we will, within about a week, we're just going to clean up this Q&A document for accuracy. So you'll have all these links to use as a resource to download off our training webpage in a PDF format within the coming weeks. So we will make this available to everybody as well. So if there's anything you wanted to say to expand upon that in question 7, if not, we can just move on to question 8 if you like.
I can maybe just very quickly, because it's such an important topic, and I'm actually really glad to see these questions about validation, about reliability. It shows us that everybody's thinking about these criteria right away when they think about the target application. So thank you for this attention. Validation of these grids obviously is a big challenge and is one of the central working parts of many members of POPGRID to think about this. How can we better evaluate the quality of these grids? Validation itself is always hard because you need reference data that you can use for direct comparison. These intercomparison experiments that are going on in the literature at the moment, there are quite some publications out in the meantime, are very interesting because they show the difference, they show the sensitivity, they show trends depending on the target application. And that's exactly the reason why this framework of fitness for use is so important, to really understand the relative quality of the data. So the user really needs to be informed about what they are using, what kind of data they have their hands on, and how to correctly apply them to the target applications.
Great, thank you very much, Stefan. And you're right, that is a big topic, so it is nice to see those addressed in the beginning of the Q&A session here. Question 8, and this is a little bit more on the application side. Could you provide some examples on how POPGRID data could be used for climate change adaptation or mitigation?
In addition to the report, which gives you a lot of good uses of the population data, there's more recent work done on modeling population movement in 2030 and 2050 based on drivers due to climate change. And this is released in a report called Groundswell Report, and I can add a link in before we release the document. So it's showing areas that are more likely to attract population and areas that are likely to see out-migration due to both climate change factors and other drivers of population migration over the longer time frame. So it's an interesting look at. It doesn't directly suggest migration, but mitigation, but it's interesting in that it shows the future patterns that are possible that you need to understand before you can do mitigation.
Yeah, great. And I posted this leaving no one off the map link into the chat window as well. And for that you referenced, or the report, we'll make sure to include that here too. It sounds very interesting.
Yeah, it's called Groundswell. Yeah, released by Season and the World Bank. And
we get this question a lot involving Google Earth Engine. Can the population data be used through Google Earth Engine?
Yeah, so I added this in because we published GPW into Google Earth Engine, and I know GHS POP has been published in Google Earth Engine, as well as World POP. So there's 3 of the data sets we talked about today that are available there. And the HRSL is not currently available, but we're actually working with Facebook and need to reach out to the Google Earth Engine folks, but we hope to put it in. The other data sets are often not in Google Earth Engine as public data sets because they have some licensing restrictions that are not suitable for use with Google Earth Engine. I can't speak on Google's behalf, of course, but this is my understanding of why not all the data sets are available. But for most cases, it doesn't stop you, if you're not aware, in Google Earth Engine, you can upload and use your own data sets via a couple different ways. So it's possible to do that with the other data sets that aren't publicly available. And I can actually add a link to documentation on how to do that in Earth Engine if you're an Earth Engine user. I just thought of that now.
Thank you. And I think question 10 was a little bit related to question 5, which was answered pretty thoroughly. So we'll move on to question 11. I wonder what population information is used in these global data sets if countries do not have updated census data. So how do you estimate the population with this level of granularity? And what is the interval of confidence at the block level data?
Yeah, maybe I can take this away quickly. Of course, the quality of these population grid estimates always depends on the input data, and the main input data source are census data. So this is a great question, and again shows us that users think about this a lot. And maybe you've seen this in Greg's demo, that when you look at population estimates coming from the population grids for different areas, you can see the input data and you can see the timestamps of what time the input data are from. So basically the time the census data has been collected, and that's really important to understand the currency of the data. Of course, if the census data are older, going in as input data, you have to be aware of this before you use the population grids for your target application. What I want to say is I'm hoping more and more that the research on population forecast and population projection will find its way more into population grid applications as well, because that's exactly one way of accounting for these deviations in currency, that you are able to project population more to up-to-date estimates. But at the moment, the user has to be very careful when using data with or that is created using input data, census data that is outdated, of course.
Great, thank you. Question 12. Presumably it's dependent on how often the sensor is run. For example, in the UK, every 10 years. Would that be about right? And it looks like that's kind of related to a question before about how often some of this is updated.
Yeah. Some countries do 5-year intercensal estimates, but roughly every 10 years. So yeah, and then there are some countries that even have an annual registry approach to census data, but they're not the majority. But in that case, they actually have annual updates to population distribution based on a registry rather than a census. So it does vary depending on the country you're looking at, but the majority is a decennial census to date.
Question 13, and this is referring to future estimates rather than just population counts. It looks like they're just looking for the different, if the grid methodology takes into account future estimates.
Yeah, I think that a number of the existing products are technically future estimates. So I talked about the Groundswell report, modeled out to 2030, 2050. The data products that are currently, released for 2020 are generally predictions rather than based on the 2020 census. And if you're interested in variables other than population counts, of course, age and sex have been done, but you can actually predict. You can use similar gridded modeling approach to predict many different variables. It's been used, I know, to predict GDP per pixel, for instance. So the proportion of gross domestic product in dollars, purchase power parity, if you're familiar with that measure, per pixel has been predicted using methods similar to what's used in some of the population models. And pretty much any variable on an administrative unit that's a count-based variable could be approached in the same method, where you look at the covariates or a simple dasometric or aerial weighting method to distribute whatever count data you have on administrative units to pixels. It's possible for any of those types of variables.
Yeah, maybe to add quickly on the idea of projections. I know that some research groups, and we are working on some population projection work that actually uses, for example, the degree of urbanization and population grids in combination to provide to create these kinds of projections over several decades, and see how these projections play out under different socioeconomic pathway scenarios. So there is research on the way that takes up these population grids for these kinds of, you can almost call it one of the applications to project population and to forecast population trends over large regions and even globally. So our hope obviously is that these data are being used for many such purposes to improve these projections as well.
Question 14, and this seems to be a little bit more regional, but you referred to Facebook population data in one of the data sets, and somebody was asking if it's available for the Mekong region yet. I'm going to post this link in the chat box so you can see it. What it looks like it is a reference to see where the population data sets are currently available for Facebook. Question 15. Urban areas have multi-story buildings with varying family sizes. Moreover, commercial buildings operating around the clock with fewer employees will also consider density. How reliable could these estimates be, and how do you adjust coefficients for different types of built-up areas? Interesting.
Oh, sorry, I was on mute. So the urban built-up and multi-story buildings aren't well accounted for unless it's unless the census data are detailed. So the present products typically use, either a simple settlement extent, or sometimes the use of lights at night from satellite drive measures helps get at this, because the more built up an area is, the more well lit it tends to be. And that's one of the covariates used in population modeling. And then there's more recent work underway to look at the volume of buildings from radar-derived data, but it's not integrated in any global or regional products that I know of right now. But I think we're going to see that approach much more common as more and more settlement extent data that has more details. So what we've seen to date is WorldPop and HRSL, both some of the newer iterations of WorldPop use a building count based on footprints where it's available, which is not everywhere. So you get a density of buildings based on count, which doesn't account for really tall buildings, but it does help look at more households possible in areas with more buildings. And then as we add for urban areas building volume, then you'll definitely see a more refined model for urban areas. This is less applicable in more rural areas where most buildings are 1 or 2 stories.
Okay, and question 16. This seems like a nice prelude to part 2, where we start to talk about some of these disaster risk reduction efforts using population grids. How can I use POPGRID to compare with natural disasters like floods and fires? What is the most appropriate data set to do that?
Yeah, I started answering this question. This is one very important target application. I'm pleased to see these questions, which is, it's really a central domain where these population grids can be and should be applied. Which one is most reliable is always a question of what exactly are you trying to do? Is it a regional approach, very local? And you have to decide what quality you need in your population estimates. What is the spatial resolution? Again, what's the operational scale, for example? I provided somewhere a link. I don't really see the question in front of me right now, to the low coastal elevation zone, a low elevation coastal zone literature. There are quite a few publications. We will update a few more of these because this is one of the classic examples of estimating how many people are actually living in coastal zones and what is the potential size of the population affected by sea level rise in the near future, for example. This is just one example. And again, you can do this globally and can make estimates for very large areas relatively quickly based on different input data, or you can transfer this to very local extents where you might want to use other data sets, other data products for population estimates if you are aware of the underlying quality and so on. So in short, it really depends on the quality of the data here, how is the data being produced, what kind of ancillary data went in there, how regional do you see the estimates that you can find in these different population grids.
Question 17, what is the name of the same project for the buildings? I guess you referenced a project that had to do with building and structures?
Well, there are two projects I know that use building structures or at least detected building presence or absence. And one's the high resolution settlement layer from Facebook, which uses the detailed, formerly Digital Globe, now Maxar imagery to detect buildings. And then WorldPop, where it's available, uses building counts as an input covariate, and it's not available universally. It's available for a number of countries in Africa, and then from something like OpenStreetMap, or not something like, directly from OpenStreetMap, they use building footprints where they exist, which is a pretty, I think, inconsistent availability and low percentage coverage globally.
This might also refer to a slightly different approach. For example, GHSL is the settlement layer that is one of the inputs for, or the input for GHS-POP, where it's more conceptualized as the built-up areas to refine basically where population has to be allocated to what kind of places, what kind of locations.
And it looks like question 18, there was great interest in the web map server demo that you did connecting through QGIS, and they had asked for the link. I believe the link is in the PDF of the presentation, but we added it here as well, and I added that to the chat. Question 19, is it possible to obtain estimated population counts by gender?
Yeah, there's 3 products that have age and sex breakdowns both, typically 5-year age breakdowns, and age by sex. So it's not available for all countries. It's available for most of the world in WorldPop, GPW4, and a high resolution settlement layer.
Great, thank you. And there was just some interest behind the teams that were behind POPGRID. And I know you addressed this a little bit in the beginning of your presentation, but it looks like you described it a little bit more here as well. Just the teams behind POPGRID.
Yeah, and I would mention the POPGRID website often lists events that different members of POPGRID may be meeting at, such as sessions at the American Geophysical Union, the American Association of Geographers, the European Forum on Geography and Statistics, and other international or US-based conferences often have different POPGRID members attending, and sometimes an organized POPGRID session like at AGU and AAG. And they're typically advertised on the POPGRID website or the POPGRID mailing list, which is noted on the website as well.
Is that a listserv that one can just sign up for?
I believe it might be an invite only. I'd have to check. Sorry, Brock. Maybe I shouldn't have.
Okay. Oh, and is there a Twitter account associated with the POPGRID Collective?
Not as far as I know, no.
Question 20.
That's a good idea.
Question 21, and this seems to really get into the details of the modeling. What is the criteria in choosing the models, the aerial or disometric?
Yeah, I had to go in and answer with this, and I included machine learning as well as aerial and dasometric. And the most important thing is how you intend to use the population surface. So machine learning approaches are less useful for inference, where you're trying to look at, why population is distributed as it is, but really useful for fine-tuning a model. Another big factor is how many input variables you want to use or have access to use. So, aerial is the simplest model and requires the fewest inputs. So you can get away with just census data, or you could add barriers like settlement extent and water or permanent ice, which is the approach we take in GPW, where it's just water and permanent ice and census data. Then you can, with Dasametric, one of the advantages, you don't need to train a model. You're building a model based on weights and assumptions. While machine learning approaches require training data, that is, ground truth validation data, which can be costly in terms of time and funds to acquire and use. And finally, I would note that the implementation and the computing resources required go up as the model complexity goes up. So you require more computing resources, more data inputs, and more knowledge of the different model approaches. So all those factors apply to selecting your model, along with also the intended audience. So a really simple model for simple global analysis is fine, but if you're trying to get very detailed distribution regionally or subnationally, you probably want to use a more sophisticated model and more data inputs.
Yeah, and maybe I can quickly add here. It's a very complex topic, and the readers will refer to some of the publications that we mentioned. Our ESSD paper has quite some resources in there. There are some really interesting survey papers on asymmetric mapping and error interpolation in general. And of course, some of the newer papers from the POPGRID Collaborative, different members, they describe more details of their machine learning approaches and how they train these different models, as well as some of the differences between models of different intensity. We mentioned this a couple of times in our presentation. This model intensity is a really important criterion, because a highly intense model, if you will, a complex model, has to be used with some care if you have not the training data, not the input data that would warrant the use of the data, as in different cases where you have a relatively simple errorly weighted or proportional weighting outcome of your data. So it's very important to understand some of the basics. Anybody who has tried to create any kind of population allocation models knows how different it can be, and how you have to be careful about the population estimates that you're creating for very fine resolution units.
Question 22, and we have about 8 minutes left, so if there's questions that we don't get to this, we'll do our best offline to fill them in, because there's been quite a few. Must be a very intriguing topic to others. If comparing and sharing data are purposes of grids, we should keep the size of the cells fixed. If so, what is the best grid site for population and dwelling applications at a global level?
Yeah, so I put in a whole paragraph here, but briefly, global data, and this is what we do in the POPGRID web viewer for direct comparison, is we've aggregated everything to essentially the lowest common denominator, which is 30 arc seconds, or roughly 1 kilometer. And then in the rest of the description, I note that the higher resolution products typically have more spatial detail in their inputs, so they've been produced at higher spatial resolutions. But for global comparison, 30 arc seconds is, if not a standard, the practice that's currently used in the community.
Good to know. So what product, question 23, what product is best in estimating population in rural areas in developing countries, especially in areas covered by forests where hosts are not often seen with medium resolution imagery, nor emit significant lights at night?
Yeah, so the dense forest cover is a problem that is not completely solved. So, none of the products are excellent at areas that are heavily forested, but the high resolution settlement layer, the HRSL, uses the highest resolution optical imagery of any of the products as an input based on 50 centimeter through to 2 meter in some areas input. So it does the best job of finding small settlements in rural areas, and has the most detail for very small settlements out of all the products.
Great. And question 24, for anybody who is not all that familiar with coding Python, it looked like you used some code in your demo. do they need to know Python all that thoroughly in order to follow along with the GitHub demo that you showed today?
They need to know Python a little bit, and if you know how to run Python, you could take that code that's available publicly and just swap in your own GeoJSON file and run it as is, and it should work fine. Yeah, I don't see any problems with that. I also noted in my answer that I typed out here that you can accomplish the same thing with QGIS or ArcGIS simply through the GUI. You don't have to know code to do the type of analysis I showed. So you could download the POPGRID data sets. They're all linked to from the website, and run zonal statistics across a subset of them and get your answers just completely through the interface.
Yeah, I think it's really important for anybody who has not made much progress on programming or any programming libraries. The data themselves are very simple. It's a simple data structure, so they are really easy to use just in a GIS environment, in QGIS, in ArcGIS, whatever somebody is using, and do some mapping, do some simple analysis, any kind of basic procedures in a GIS environment. So anybody who has not seen these data should be encouraged to download them and play around with them and look at them. They are all freely accessible.
Great. Question 25, we seem to have lost the question, but we have the answer, so maybe we can infer what the question was. So I guess what you were alluding to here, I'll let you take it.
Yeah, sorry, I don't think I deleted the question, but maybe I did by mistake. So from what I recall, the question was, I made the reference to the paper by Thompson et al. that talks about how slum areas are underestimated in global products. And the take-home message would be that it would be best to use survey data where available to get at either total population or household size to estimate population distribution in slums. Unfortunately, there's no good global source of survey data from slums, but you could train a model to predict it in areas. But again, that would require knowing where the slums are. So this is something best done regionally or subnationally, at a city level or a country level, where you've got ancillary data on the location of the slums so that you can do a better job of predicting the population.
Okay. And question 26. What ancillary data can be taken as a proxy for sparsely dense grid and vice versa? Since road networks, lighting, built-up areas may be ambiguous to represent actual density. The example here is slums with a lesser road density will have a greater population than the organized office area with more lighting and greater road density and built-up. I have a long question here, but
yeah, it relates back to the previous question, and I'm sure Stefan or somebody else could provide detail, but I would definitely talk about survey data that give you an estimate of the density, like average household size inside of these areas that are less well populated. It's when using the more sophisticated models, these data don't have to be available everywhere. They can be used to predict it. The higher densities in areas that represent it. But it is an ongoing issue, and it is an area of active research, so we don't have a complete answer.
Yeah, and I think it's a great example where the problems might actually exist in these kinds of models. Imagine there's a model that's really calibrated towards intensity, nightlight intensity, or road network density, etc. A big proportion of the population would be miscalculated, obviously. So in such a case, it would be very important to know about some regionally different constraints, how the model has to be calibrated, what kind of input variables would be available, what kind of new global data sets can we use as additional ancillary data as constraints and so on. So it's a great question and a good understanding of exactly these kinds of problems inherent in the final outputs and the final data products. Thanks for the question.
Great, thank you very much. And this will be the last question that we'll take here during the live Q&A. And How accurate is the low elevation coastal zone data for small island developing state like the Bahamas? What data set would you recommend being used? I'm not sure if you showed this in your presentation, but are there some elevation data that's used through CDAC and put together with these?
Yeah, I mentioned the low elevation coastal zone study that was a global study done using SRTM to define the coastal zone. And SRTM is a good, consistent global data set. But in small island states, what would be ideal is if you can obtain local elevation models to define your coastal zone. So whether it's from the Bahamian government or it may be possible to get even LiDAR derived, which is light imaging detection and range LiDAR data, which gives you a much more detailed look at the coastal zone distribution. And then you could, from LiDAR data, you can even pick up structures and start to look at an analysis that tells you how many buildings are inside the coastal zone. So locally available data may always be better than this global SRTM coastal zone data set that we've defined. But we've provided it in part to look at a global assessment and international comparisons. So it's useful for that level, but for local single state studies, you probably want to see if you can obtain much more detailed data. And then you could take the methodology we used for defining the coastal zone and refine it based on the more detailed data and get a much better picture of population or even structures at risk to sea level rise or more frequent storms.
Great, thank you very much. So that was the last question for the session here today. To any of the questions that we didn't get to, please feel free to email me at my email address here or the general ARSET Gmail account that you see all of your communications from us. And I can direct those to the appropriate personnel to maybe address those, or we'll get to the questions when we post this online in a week. And hopefully we've got to all of them there. We thank you very much for joining us here today. Greg, Stefan, this was wonderful. I hope that you learned a lot from the question and answer session too.
I did indeed. Thanks very much. Thanks, Stefan.
Yeah, we had some great questions. Thank you so much for all this interest. Really appreciate it.
Yeah, and so I just want to say that so next week, same link to join, same time, we'll be meeting for part 2 of the series, the final part. At the end of that one, we will have the homework available for you. It'll be a Google form, and that will be due April 27th. So we'll post this recording with the Q&A in the video by tomorrow for you to review. And please join us next week, where we're going to talk about some specific applications of the population data grid. So thank you very much, Stefan and Greg.
Thanks for having us.
Thanks very much. Have a good day.